you and say, look, you learn more from your failures than from your successes.
Specifically,
in some ways, this has some resonance.
Good morning. How's everybody? Thank you for the kind introduction. It's true. At daytime, I work with technology, and at nighttime, I make art. And I'm going to tell you a little bit about art and technology. Art and technology have interacted in interesting ways throughout the ages. One such example is photography. This is probably the first photograph ever taken. It was taken in 1826 by Joseph Niepce, and he was experimenting with light-sensitive materials to capture projections from his camera obscura. At the time, the only known way to capture sort of an accurate picture of anybody was painting. And since the Renaissance, most of progress in painting was focused on accuracy. So perspective and light, shadows. By 1838, Daguerre had improved on the technique by using polished silver plates treated with iodine. And you can see, essentially, he succeeded at mechanizing the process of taking an accurate picture of reality. A year later, Paul de la Roche, a French painter, declared, "From today, painting is dead." And you know, he was right. After that time, there were no significant paintings at all. Or this, or this. By the middle of the 20th century, art had essentially been liberated from the role of making accurate representations and free to go and explore incredibly interesting new ways of depicting things. The Kodak process, in the meantime, commoditized photography, and people started very quickly making art. And indeed, today, fine art photography is alive and well, with hundreds of millions of dollars of revenue and turnover in terms of art sales. And indeed, painting has sort of come full circle. There are now techniques such as hyperrealism, which incorporate photography as part of the painting process. Okay, something completely different. Neural networks. Neural networks are a form of computing which has its beginnings in the 40s, when people started thinking about the brain as a computer and thinking about how it might work. And for example, one of those people was Alan Turing. In a not very well-known essay from '48, he proposes a computing architecture based on the idea that you could have these very simple units, like neurons, which would make very simple calculations based on connections from other neurons, and that the connections would be tunable, essentially. So his idea was that this machine would be at first unorganized. He called this a B-form unorganized machine. And then through training, it would organize itself in order to do the task at hand. I guess I should also say, people have built these machines, and they started working okay, but in most of the 20th century, I guess the sort of expert system and rule-based systems were better at solving difficult computational tasks, for example, computer vision problems or other like language translation and parsing. But in the last 5 to 10 years, there's been an incredible revival of neural networks in this field, and indeed most sort of cutting-edge technology in this field now uses neural networks. Part of this change was algorithmic, and part of the change is that we have more data now, but a big part of this change has been the commoditization and sort of the advent of cheap parallel processors, which are very good at the kinds of calculations you need for neural networks. So to give you a very quick idea, in 2000, the fastest computer in the world was a building, cost $110 million to build, and consumed 6 megawatts of electricity. Just 15 years later today, you can buy a GPU accelerator card, which produces the same amount of computational power for just $1,000. And it's about this big, and you can put it into your computer on your desktop, which means anybody can play with this kind of technology now. Okay, so very briefly about neural networks. They're composed of simple units. Each unit usually does a very simple calculation, like an addition or an application of a simple function. It takes input from many other neurons and sort of agglomerates that data that comes in and sends it downstream to other neurons. And these things are connected in a kind of network. This example here is a classic computer vision problem where you have pictures and you want to basically classify the pictures. You want to have a computer program that can tell whether a picture is a picture of a cat or a dog or whatever. So when you try and solve this kind of problem with a neural network, this kind of architecture is often used. It's in layers, where each layer only connects to the next layer. The information from the picture, the pixel data, is fed into the input layer, and then the next layer sort of takes that information and processes it and passes on to the next layer. The weights that connect the neurons the connections that connect the neurons have weights associated with them, and those weights are random at first. So just like Alan Turing proposed, at first this machine is unorganized. It doesn't work. If you show it a picture, it will randomly give an answer on the other side. By the way, typically on the far side of the network, you have sort of fewer and fewer neurons. And at the end, you might just have a very small number that represents sort of the results, the target classes. In this case, it would be 2, say, cat and dog. And when you feed information through the network, it runs through like this, and then you get some answer. Now, at first, this doesn't work. We need to train the network. And this is basically the essence of the thing. These kinds of machines are capable of extracting the salient features from any kind of input data, in this case, pictures. So we would show the network thousands and thousands of examples of cats and dogs, and each time we would tell the network, this is a cat and this is a dog. And if it gives the wrong answer, which at first it will do all the time, you adjust the weights of the network in such a way as to elicit the correct answer more likely. And if you do this over and over again in an iterative way, you end up with a computer program that can distinguish pictures of cats and dogs even in cases where it's never seen that particular pictures before. And that's kind of the point. It generalizes what makes a cat and what makes a dog. Now, what's remarkable is that it self-organizes in such a way that the layers that are close to the input data, basically the neurons in those layers become reactive to simple features like edges, corners, or combinations of them. And then as you move through the layers, the features that the neurons respond to become higher and higher order. So maybe they would react to like a longer line or a square, and then further up they might be complete features like a hubcap or an eye, and then right at the end of the network, the neurons respond to really complex features like a cat. Interestingly, people have found very, very similar things in our own brains, in the visual system, through different layers, also extract higher and higher order features. Once you have a network that's trained this way, it should be possible to also run this thing backwards. If you have a thing that knows everything about what a cat is like, it should be able to produce new pictures that look like cats or dogs. And so these are called sort of generative neural networks. And I'm going to show you a couple of examples of this kind of neural network. One of them started with experiments by Alexander Mortvintsev at Google. He was interested to create visualizations of the internal knowledge sort of stored in the neural network. And he came up with this really neat algorithm where you show a network that's trained on whatever, a picture, you run the network forward, and then you basically say, okay, whatever you saw, we're going to adjust the pixels in the image towards that interpretation, just a little bit. And if you do this over and over again, you get these kinds of images. Suddenly, the photograph fills with all these interesting impressions that the neural network knew about. It's almost like cloud watching. The slightest suggestive features suddenly turn into dog faces and cars and buildings. So when I saw this, I got really interested. As an artist, I thought this would be really interesting to use to make art. And the first thing I tried was, well, what if we just start with random noise? And also, what happens if we sort of keep zooming into the picture? And this is what I found. So you get this really interesting sort of fractal world appear, where the network keeps over-interpreting and over-interpreting the image. This keeps on going forever, essentially. You can just keep going. What's interesting, too, is that depending on where you do this in the network, it reveals sort of the level of the kind of features that that layer cares about. So the early layers, like I told you, care about very simple features, lines and edges and so forth. And you get pictures that are composed of those kinds of things. As you move through the network, you get higher and higher order features, windows, or mountain ranges, or entire concepts like buildings or trees. So these images are just sort of spewed out by the network based on the rules that it extracted from natural images that it saw during training. You can also ask a different question. You can say, okay, well, what does this one neuron care about? Like, what does it respond to? So if you optimize images with respect to a single neuron, you get much more focused kind of things. So this neuron cares about pictures, apparently, or artichokes, or wine bottles. And if you look at these kind of pictures in detail, you realize that they're actually not full-blown concepts. They're more like these impressionistic like bags of likeness. So you probably recognize this as turtles, but if you look closely, there are no turtles in this image, only turtle-like things, turtle-like features. And it is in your brain that you complete that illusion. You also get really interesting artifacts. So during training, evidently, all musical instruments were shown with the person playing it. And so the neural network thought, well, it must be part of the musical instrument. And so when you visualize them, it paints the musician in with it. OK, so images. What about prose? Same thing. You can train a neural network on text, and sure enough, it will produce more text like it. So in this case, this is work from Ryan Quiros from the University of Toronto. The neural network says, only Prince Darren knew how to run from the mountains, and once more he could see the outline of a rider on horseback. The wind ruffled his hair in an attempt to locate the forest. He hadn't been in such a state of mind before, but it was a good thing. The wind blew up the mountain peaks and disappeared into the sky, leaving trails behind the peaks of the mountains of Mount Fuji. Text generated by a computer. I don't know why. This is the interesting thing about neural networks, but that's what came out. Original content from a neural network based on data. Music is another example. If you play lots of classical, say, piano music to a neural network, you can also produce new music. This is work by Daniel Johnson. Piano music composed by neural network. It's very important that we don't anthropomorphize these systems. It's very tempting to do, I know. We always use words like, oh, this thinks, or this dreams, or interprets, or whatever. You have to remember these are really simple algorithms in many ways. They're just algorithms that can extract patterns from data, very large amounts of data. There's a history of people trying to build creative machines. David Cope's experiments in musical creativity, for example, or in this case, Harold Cohen's Aaron, which is an algorithmic painter. And a lot of these are based in sort of slightly older techniques like expert systems, but the principle is the same. People have been trying to come up with technology to sort of generate original content. And it's hard. It's really hard. And it's been incredible forays into this area. And it asks really interesting questions about our own creativity, about human creativity. And sometimes also people like to sort of spell doom for the arts. And I, just like with photography, don't subscribe to that view. Instead, I think actually these kinds of technologies can be used by artists, human artists, to create new and interesting works. And also I think it asks us to come up with even harder, even more interesting stuff maybe that machines cannot do yet. Machine learning is really transforming the world in incredible ways. Self-driving cars are a reality today. people using machine learning to do diagnoses of cancer, and all sorts of other applications. And the applicability of neural networks for data mining and analysis in these kinds of applications is pretty obvious. But what's not obvious to me is exactly how do we use these kind of networks for the arts, and what effect will it have on the arts? I feel in many ways, just like at the time when Niepce was experimenting with photography, we don't really know, we've really barely just scratched the surface. Like, we don't know where we're going yet. These are very simple toy examples that I showed you. But it's a very exciting time. I often feel when I experiment with these kind of methods, I feel like a monkey, sort of banging rocks together, thinking like, okay, there's something here, I'm not quite sure. But I'm incredibly excited about this as an artist. And I'm very excited to see what other people do with this technology. And I'm sure we'll see really interesting examples come out of the art world that incorporate technologies like neural networks. Thank you.